Welcome back to the deep dive. Today we are wading into a topic that's generated just a massive amount of hype, maybe some controversy too, and definitely investment dollars. We're talking about large language models, LLMs.
Right, LLMs. And it's a field that feels defined by complexity, doesn't it? You hear about billions of parameters, these transformer architectures, self-attention.
Well, exactly. All that jargon. It
Yeah.
really acts like a huge gatekeeper for anyone just curious, trying to understand.
It does. The barrier to entry for, genuinely getting how these things work feels incredibly high.
But you shared a really interesting source with us, AI in 10 minutes, how large language models actually work. And it sort of promises to cut through all that noise. So our mission today is kind of twofold. First, let's try to distill the core knowledge of LLMs, quickly. And second, let's really analyze the specific approach this source uses to make that knowledge stick, because that seems key.
Yeah, and the description itself highlights three things it relies on. It calls itself a simple explainer, it uses visuals, and leans heavily on everyday analogies.
Simple explainer, visuals, analogies.
Okay.
And for that learner profile, we often talk about someone who needs speed, needs clarity, but also wants some depth. That combination, that methodology, seems like a perfect blueprint.
I think that's the real insight here, actually. We're not just deep diving into LLMs, but into the art of explanation, of distillation itself.
Precisely.
So the big question then is, what makes an explanation of something so mathematically dense, like an LLM, both simple and memorable? Where do you even start?
Well, let's unpack that by looking at the most, let's say, aggressive constraint right in the title, AI in 10 minutes.
10 minutes, yeah, that's brutal.
It is brutal. And what it does is it forces you to just completely leave out huge amounts of technical detail. You simply don't have time.
It's like the ultimate filter, isn't it?
Yeah.
If you have to fit it into 10 minutes, what are the first things you just ruthlessly cut? And maybe more importantly, what are the absolute essentials you must keep? Okay, so what you cut generally are the deep how it learns details, things like backpropagation, gradient descent, those specific optimization functions like ReLU.
The real nuts and bolts under the hood.
Exactly. The architectural mechanics. They aren't strictly necessary for a functional understanding. What you absolutely keep are the fundamental concepts of how it operates.
That's what we do.
Prediction, sequence processing, and tokenization. I mean, in 10 minutes, you absolutely have to establish that an LLM is, at its core, a probability engine.
Sure.
It's predicting the next chunk of text, the next token in a sequence. If you, the learner, grasp that central idea, you grasp the core mechanism.
Let's pause on token right there because that word gets thrown around constantly. If the goal is clarity, how does a good 10-minute explainer define token simply?
Right. A token is basically the unit the model predicts. It's the level it works at. And crucially, it's not always a full word. It might be punctuation, a space, or even just a common part of a word, like ing in running.
I see.
So by focusing on tokenization, even briefly, the explainer immediately shows you that the model isn't thinking in these beautiful, complete sentences like we do. It's thinking in, well, statistical fragments.
That really reframes the whole thing, doesn't it? The time constraint forces that clarity about the model's most basic operating unit.
It does.
And if you understand that prediction aspect and this idea of tokens, you probably have the foundational knowledge you need for, say, most water cooler conversations or even basic meetings about AI.
Exactly right. That forced distillation is the synthesis bit. It packs the information into the absolute minimum required for that functional understanding. It respects your time by delivering the critical path first.
Okay, so that leads us nicely to the second element the source mentioned.
Yeah.
The need for everyday analogies. Given that LLMs are really just, millions or billions of numbers on a server somewhere, this abstract mathematical black box, why are analogies so critical? Are they the only way in?
I'd argue they're the most effective bridge, certainly, because an analogy maps that foreign complex process onto a mental model you already have.
Okay, give me an example.
We'll take word prediction. If I start talking about probabilistic sequence processing based on transformer layers, your eyes glaze over, right?
Pretty much immediately.
But if I compare it to the predictive text feature on your phone.
Okay, I know that.
Right. But imagine that predictive text running at a scale so vast, it's essentially read, well, a huge chunk of the internet. Suddenly, you have a handle on the function, even if the scale is mind-boggling.
Hang on. Here's where I feel like I need to push back a little. Doesn't simplifying it that much, just saying it's a highly advanced predictive text engine, doesn't that actually miss the magic? Doesn't it undersell the deep learning part, its ability for more complex reasoning or synthesis?
That is a fantastic challenge, and it points directly to the inherent risk in any analogy, right?
Yeah.
Oversimplification.
Yeah.
So a good explainer, even a short one, has to anticipate and address that risk. The simple predictive text analogy gets you, let's say, 80% of the way there for understanding the basic output mechanics.
Okay, 80%. What about the other 20?
To cover that remaining 20%, the complexity, the nuance, you need a slightly more sophisticated analogy, one that explains the contextual awareness of the model.
Contextual awareness.
Yeah.
And what's the key technical concept that analogy needs to map onto?
It really needs to cover the attention mechanism. You could argue this is the most important innovation within that whole transformer architecture.
Okay, attention. What does that mean practically?
It means the model needs to figure out which parts of the input text are most relevant when it's deciding on the next word.
Right, like your example earlier. If I start a sentence, the bank was so steep I couldn't climb it. The model needs to figure out if bank means riverbank or financial institution.
Precisely. And that's where a better analogy comes in. Maybe compare the attention mechanism to being in a noisy room. The model has to sort of listen selectively. It has to prioritize the important voices, or in this case, the important words in the preceding conversation or text, to understand the context. That's where the aha moment can happen for the learner.
Ah, I see. So the analogy helps us grasp that the model isn't just looking at the immediately preceding word, it's actually weighing the importance of all the previous words to figure out the context.
Yes. It's assigning different weights, different levels of importance, that capacity for context, and essentially a form of short-term memory achieved through this prioritizing mechanism. That's the function you need to grasp.
And that feels like a huge lead from just comparing it to my phone's autocomplete.
It is. And the analogy is the cognitive shortcut. You don't need the linear algebra behind calculating attention scores. You just need the concept. The model pays attention, it weighs importance, it builds context.
Okay, so we've got the time constraint forcing focus on prediction and tokens. We've got analogies helping us relate abstract functions like attention and context to things we know.
Right.
So once you've built that functional understanding, how do you make sure it actually sticks?
That seems to be where the third element the source mentioned comes in, the visuals.
Visuals are, I'd say, almost non-negotiable when you're dealing with systems based on complex structures or flows. Think about it. If you just read a description of the transformer architecture.
Encoder, decoder, self-attention layers, feed-forward networks.
Yeah, it's just a list of jargon, even if you've explained the function.
Exactly. It's like reading the assembly manual for a complicated machine you've never actually seen. It just doesn't click.
Right.
But the moment you introduce a visual, even a simplified diagram, you transform that abstract list into a kind of structural map.
What does that map show?
It shows the flow. You can see how the input sequence, the text you type in, gets broken down into those tokens we talked about.
Okay.
You can see how those tokens travel through the system, maybe hitting multiple layers stacked on top of each other.
And what are those layers visualizing? Is it just complexity?
It's visualizing the depth of the processing. The model doesn't just look at the input once. It processes it, refines its understanding multiple times through these stacked layers. A text explanation can say many layers, sure.
But the visual lets you see it, like a funnel data goes through.
Sort of, yeah. It shows how the data is transformed repeatedly before that final output prediction is made. It makes the abstract process feel much more concrete.
And that visualization of flow gives the learner something tangible to hang on to, something to recall later.
Definitely.
Like if you can mentally picture or even roughly sketch that data flow input on one side, prediction on the other, those attention layers stacked in the middle, you've essentially internalized the high-level architecture without needing the blueprints.
And that visual element significantly boosts memory retention. When you recall that diagram, maybe it had colors showing different parts or arrows showing the flow.
Yeah.
You're tying the conceptual understanding you got from the analogy, like attention means focusing, to the structural reality shown in the visual. It links function and form.
Okay, this feels like the synthesis moment. We've looked at the structure of what makes this kind of explainer successful, that tight time constraint forcing focus, the analogies making function relatable, and the visuals cementing the structure. So let's bring it back to the listener. What does this specific approach really mean for you? How can you leverage this learning framework when you encounter any new complex topic, not just AI?
I think it means realizing that being functionally well-informed enough to discuss something intelligently doesn't always require deep, deep technical expertise. It often requires mastering this art of, let's call it intentional simplification.
Intentional simplification. I like that.
The core insight is that for any complex system, you should always seek the simplest, clearest path to understanding its core function and its basic structure. What does it do, and roughly, how does it do it?
So the so what for the listener is really about prioritizing. When you bump into something complex, maybe it's quantum computing, maybe blockchain, whatever the questions to ask yourself immediately are, what are the, say, 2 or 3 things I absolutely need to know to talk about this?
Right.
And what's the best everyday analogy I can find or create to explain its core action, its main purpose?
Exactly. You're searching for that clear structural map, even a basic one, and that fundamental metaphor or analogy. If you can roughly diagram the process flow and explain what it achieves using a non-technical comparison, you are genuinely well on your way.
It kind of reframes what it means to be well-informed, doesn't it?
Yeah.
It's less about memorizing facts or code and more about achieving that access to understanding and being able to retain it.
Precisely. It's about grasp, not just recall.
This has been really fascinating. It's a look not just at LLMs themselves, which are complex enough, but also at the methodology behind how we can learn about any complex subject more effectively. So thank you for walking us through that distillation process.
Yeah. Oh, my pleasure. It's a crucial skill in today's world, I think. And maybe as a final thought, something for you, the listener, to explore on your own, building directly on what we just discussed.
Okay.
Given that we've established the LLM's core function is predicting the next token, those little statistical fragments, not always whole words.
Right, the fragments.
What do you think is the single best, simplest, everyday analogy you could use to explain that specific concept, granular statistical token prediction, to someone who knows absolutely nothing about AI? Think beyond just predictive text. How does language itself break down in that prediction engine?
That's a great challenge to leave us with. How do you explain the granularity simply?
Okay.
Lots to think about there. We've reached the end of this deep dive into making the complex accessible.
Always a pleasure.
We'll catch you next time.